Hi everyone, welcome to Data Umbrella's webinar. I'm going to introduce Dorota to do an overview of R-Ladies, then I will do a short introduction to Data Umbrella, and then I'll introduce our speaker for today, who's Mitzi Morris. So welcome, Dorota.
Thank you so much. Can everybody see my slides okay? Yes? Okay, wonderful. So I'm here representing R-Ladies New York, and I have a few slides here. There's two things I'm going to talk about. I'm going to talk about the global R-Ladies organization and then the local New York chapter. So what is R-Ladies? R-Ladies Global is a worldwide organization that promotes gender diversity in the R community via meetups and mentorships in a very friendly, welcoming, and safe environment. It's been a really wonderful experience for me to be a part of, so much so that I ended up joining the board of my local chapter because I really wanted to give back to this wonderful community. So the mission is to encourage more women and non-binary coders, developers, speakers, and leaders in the art community and just in general in the programming world. More diversity and equity and inclusion of people developing art packages and being part of the wider art community. And this is a map. At this point, I think this might be a little outdated, but we have chapters all over the world, and there's always more coming. So it's a really beautiful, just very inclusive community to be a part of. If you are interested in starting a chapter in your city, you can reach out to info@rladies.org to get in touch. But they're really all over the place. So you might already have a chapter nearby. And as I've mentioned, I represent New York City. And New York City, this chapter was founded in 2017, which was a few years after the first chapter was founded in San Francisco. I am a co-organizer amongst several other wonderful folks. And a few fun facts. So we have over 3,000 members on Meetup at this point, which seems like a lot. And it is a lot, but our meetups don't end up being huge. People just, come as they can. And so it's not, don't be overwhelmed by that big number. Come and join us. It'll be a good time. We host monthly events. And if you are curious about us and our events that we're hosting in New York City, please check out our website at R-Ladies NYC.org. We have meetup talks, we attend conferences and workshops, we host book club events, and just networking and social events, which are always a blast. And some ways to get involved is to obviously attend our meetups. You can also follow us on Twitter. We have a Slack channel and GitHub pages, so you can reach out to us via that. We also have a blog on our website that you could write a blog post for if you are interested in doing that. Or you could give a talk. We're always welcoming even new speakers who haven't presented before. It's a really great opportunity to share your knowledge and skills and practice your presentation skills. And again, you can always sponsor a local chapter if you don't have one nearby, or join the board of a local chapter to help them out. And to spread the word, tell your friends. It's a really wonderful organization to be a part of. And that's it. Here's some contact information in case anybody is interested.
Thank you so much, Dorota, for that presentation. I will now give a short presentation of Data Umbrella and then introduce our speaker. So this talk is being recorded and it will be available on our YouTube channel in the next 24 to 48 hours. So Data Umbrella is a community for underrepresented persons in data science, and we are a non-profit organization. The Data Umbrella team, we have a team of volunteers who work together to bring events to you related to data science and open source. And today we also have Reshma on this call, who is a community manager and the director of Data Umbrella. So we have a code of conduct and we are dedicated to providing a harassment-free experience for everyone. And we thank you for helping make Data Umbrella a welcome community for all. So there are different ways in which you can support us. So one is by following a code of conduct. You can also share our events with others. And then you can also contribute to Data Umbrella through open source. So we have different ways you can contribute. For example, you can contribute to timestamps. After we upload this video, we have timestamps instructions on our GitHub page where you can contribute to the timestamps of this video. We are also working on our new website. If you have any skills that might help us with that, you are welcome to contribute to that as well. Apart from that, we are developing an events board as well. You can go over to our GitHub. We have instructions on different ways in which you can get involved. We also have a blog. So if you have participated in our events before and you have feedback for us, then that would be helpful. We are also on Open Collective, where you can donate to our nonprofit, and also on Benevity, which is a company match platform, where if you donate, your company matches the same donation. We also have a YouTube channel where we have the videos to our previous events. You can catch events videos there. We also had Mitzi present to our community 2 times before. So if you're interested or you would love to hear some of her talks again, you can go back to our YouTube channel. We have different playlists. We have playlists like career advice, data visualization, contributing to open source, and data science for beginners. We also have a monthly newsletter on Substack where we release once a month, and you can sign up for that on substack.com, and we promise not to spam you with too much emails. We also have our website, dataumbrella.org, which has resources. So we have lists to conferences, open source resources, guides to inclusive language. We have resources on burnout, AI ethics, and more. We are across all social media platforms. So Meetup is where we post all our upcoming events. YouTube is where we post all the videos to our previous events. GitHub has instructions on how you can get involved in open source. And then we also have Twitter and LinkedIn. We have a job board, which we update regularly. Or if you have a job that someone your company has open, you can also help us by posting it on our job board. And as I said, we are on Open Collective where you can donate to us as well. We have live captioning for this event. So if you need to use live captioning, then at the top of your screen, we have a button labeled CC. Feel free to use that as well. We have an online suggestion box. So we have a form which have the link on the handout section where you can have suggestions for future event topics. If you're a speaker and have a topic in mind that you would like to talk to a community about, feel free to sign up there. We also welcome feedback for this event and any other feedback generally on events you would love to hear. We also have an upcoming event next week on blockchains for open source solutions. Feel free to join that as well. The event is listed on our Meetup page. So on today's event, we have lessons from COVID-19, where we look at random and non-random missing data and its consequences. Our speaker today is Mitzi Morris. Mitzi is a member of the STAN development team, working at Columbia University for Professor Andrew Gelman since 2017, where she's helped develop and maintain both the core C++, command STAN, and Python CMD StanPy interfaces. So in collaboration with the STAN team and epidemiologists, she has developed STAN models for spatial epidemiology. You can find her on GitHub. There's her GitHub link. These slides are available on the handouts section if you want to connect with Mitzi. And with that, now I take this opportunity to welcome Mitzi so that she can continue. Welcome, Mitzi.
Hello, everybody. Oops, let's go back to the start. Okay, can everybody see this? So I'm very happy to be here today, and I'm talking about lessons from COVID-19, non-random missing data and its consequences. Thank you, Beryl, very much for that introduction. I am a member of the STAN development team, and I'd just like to say that as the about me, I think Beryl pretty much said it all. During COVID, we were, all members of the STAN team suddenly became very popular because there was a lot of data and it was very noisy, and the people to whom the data most mattered really were not used to dealing with that much data and that much uncertainty in that little data. So reaching out to members of the Bayesian community made perfect sense. And so also we're really going to be looking at some COVID-19 data. So I hope that none of you were too deeply scarred by the events of March and April and May of 2020, because that's where we're going. So the paper that I want to talk about is a really great paper that I think we can work through. So this talk is going to be somewhat me presenting this paper. There's not going to be any demonstrations per se, no STAN code, no R code. I want you to be able to understand what is being presented in this quite technical paper on archive, because the ideas are incredibly valid and necessary. So first, we're going to look at the COVID-19 pandemic as it played out in Michigan. Then we're going to have a little bit of a background about missing data, because this talk is generally applicable to situations where you have a lot of data that's missing, critical missing data. And then we're going to look at the paper, which did a beautiful simulation study to bear out their thesis. And then we're going to look at the actual models presented in this case study, in this paper, modeling racial ethnic differences in COVID-19 incidence with covariates subject to non-random missingness. So let's talk about COVID-19 in Michigan. And the paper, the Trangucci paper, is only covering the initial period of the pandemic. Unfortunately, in a pandemic situation, the initial period will be critical and stressful because it's a new unknown situation with respect to the particular disease. But what I'm hoping to bring to the community here is an understanding of what happened during COVID so we can be better prepared next time. And I also forgot to mention that Rob Trangucci is a STAN developer. He used to be working with the STAN team here in New York, and he's just finished his PhD at the University of Michigan and will be taking a faculty position at the University of Oregon starting this month. So let's talk about Michigan. What we have here is the final tally from the New York Times tracking coronavirus information set. And I've put bright red arrows under these timelines because all we're looking at is this very initial peak here of the test positivity rate, the hospitalization rate, and the death rate. And if you look up here, this is all cases from all time. And in the beginning of the pandemic, we had actually, compared to how things got with here, this was, I believe, Omicron Christmas, if you remember that. oh, and this was Delta summer. But this was the first year of the pandemic when everything was first coming online. We just had gotten PCR tests, which would let you determine whether or not you had COVID. And the vaccines did not become available until the following spring. So this was a pretty awful time for all of us who were there. And what you see is that the test positivity rate was very, very high, only because there were very few tests available. The people who were getting the tests were the people who were already in the hospital, by and large. The hospitalization rate was very high, and the death rate was extremely high, because at that point, the hospitals didn't really know. They didn't understand the disease, they didn't understand the treatment, and they didn't understand what needed to be done. So it was a very awful time. And what was established a year or so later is that there were pretty bad racial disparities in the mortality rates. So this is a study also just from the data available in Michigan. And it covers a longer time frame instead of the first 3 months, which is what's reported and simulated in the Trangucci paper. We're going for the first 6 months. And their conclusion is that the mortality rate for Black individuals was 3.6 times higher than that of white individuals. And then there's a second very awful looking estimate that we could possibly say was not as starkly awful as this would indicate, because the people who died from COVID under 65 who had no comorbidities, that was a very, very small fraction of the deaths. So we're looking at the ratio of two estimated rates for a small population. This is a very, very variable estimate, but it sure looks bad. Now, all along in COVID, so during COVID, I was working in conjunction with Bob Carpenter, another STAN developer who just happens to be my husband. We were working together with people from the UK who worked at the National Health Service, and they wanted to know what everybody wanted to know. What is today's infection rate? And what do we think next week's infection rate is going to be? And you need to be able to estimate trends 1 or 2 weeks out, because if you're a public health official, what you're trying to do is you're trying to alert the policymakers as to what you need to do. Where's the hot spot? Should we restrict public gatherings? Should we do something? Should we send people out? Who needs the resources? What can we do? And the best way to estimate what the infection rate is today is to look at yesterday's PCR test data and to try to draw inferences from the test data for what's going to happen next week. The problem in this situation is that as the waves of the pandemic roll through the population, the demand for testing increases pretty rapidly. And the higher demand that you have for these public health resources, the more the data that's collected becomes spotty. And the harder hit and the more under-resourced the area that's collecting the data is, the more you're going to have missingness. And given that we know that there are large socioeconomic disparities across our society, what happens is that the missing data is coming generally from poorer, more understaffed, less resourced facilities, and that's where certain populations are. That's where the under-resourced populations are. It's basically socioeconomics, which correlates in the United States extremely highly with what we call race and ethnicity. So this was definitely a public health care crisis, and the data collected and the estimates coming out. I'm sorry, I'm suddenly seeing some screen which says, are people able to write in the chat? Okay, sorry. Technical difficulties. So anyway, let's move on to what's going on. What we're talking about today, and this is a general topic, which is missing data. So data, when you're collecting when you're doing any kind of data collection effort, you're going to have your outcome, what you're interested in making estimates about, and then you're going to have a number of features of that outcome that you're collecting. So that's what we're talking about, the data here. The data is all of the features that accompany your observation that you care about. Now, if any particular data item is missing just because there's no pattern, you could call it really truly random white noise, then you have data which is missing completely at random, and that should be okay if you do without that data item, because it's not going to unbalance your data in any way, shape, or form. If your data is missing at random, but it is, well, the missingness is not random, but you could infer the missing data from other of the variables that are present. So the canonical example, the example used in the Wikipedia article is, say that you have a survey and you're trying to do a mental health assessment and you're asking questions about how do you feel. And you're getting far fewer responses from those people who are identifying as men in the survey, because in general, men don't really like to talk about their feelings, so they leave that little detail off. Well, then you might be able to impute some general pattern of how are you feeling if you're a man, given the fact that you're a man. Now, if you have a non-ignorable non-response, data that is not missing at random, then the value of the variable, how you're feeling, is directly related to the reason that you're feeling that way. It's not just because you could be feeling any old way, but gosh, because of who you are, you don't like to talk about your feelings. It's because you're not talking about it because that's the way you feel. So that's our Wikipedia article. There's a link to it. You can go there. And the more that the data is not missing at random, the more biased are the estimates that you're going to get out of your model for the phenomenon that you care about. And just to get a little bit of terminology out of the way, what we're talking about when we're talking about strata and stratum is that we have a grouping of the data based on a categorical variable. So for any kind of population which is relatively diverse, we want to look at subsets of the data because we want to know about specific subgroups. And if the data is very diverse, without accounting for if the data is overall heterogeneous, but that one subgroup has a particular pattern, well, then you just want to look at that subgroup to get a very clear focus on that pattern. Doing it in a Bayesian hierarchical modeling paradigm will allow you to get more information about generalities through the hierarchical structure of your model, which lets you share information so you can really laser in on what's going on that subgroup while getting a little bit of general information from what's going on in the population as a whole. In the Michigan study, we have age of of the people who got COVID, we have that binned into 9 different levels. And then we have the sex assigned at birth, 2 levels. And then for this particular study, they had data from 13 different areas, which are the various zip codes, I believe, or census locations within the county of Wayne, Michigan. And then we have 4 levels of ethnicity, which have been aggregated from various kinds of response, because tabulating race ethnicity is a little bit complicated. So in the paper, by and large, when they talk about a strata, they're talking about an age-sex strata. There are 18 of them, 9 age levels by 2 sex levels. And you want to, when you're doing this kind of stratified estimation, the most fine-grained level of stratification is just blowing it all out in the Cartesian product of all the possible values of all the features you care about. So for age by sex by location, we have 13 zip codes or 13 census areas, and that gives you 234 strata. And if you were going to blow it out by making estimates on a per sex, on the whole of your data, looking at what's going on for a given age, sex, in a given zip code by a given race, you would have 936 strata. And what they do in this paper is that they do a very convincing simulation study to demonstrate that the COVID data, which has, that if you have data that is not missing at random, you need to have a model which accounts for that non-random missingness. And so what they do is they create 200 simulated data sets. And in those data sets, the racial race ethnicity, that particular variable, is sometimes missing, and it is not missing at random. So the data set construction, because we're going to do a COVID prevalence simulation study, for all of the strata, for all of the races, you're going to have the same COVID incidence, and you are going to have varying amounts of known fully specified cases. That is, cases where you have age, sex, and race, given that you have COVID. And the rate of COVID does vary according to the age sex strata. So the older you get, the more likely you are to have COVID. And I believe there was a sex difference in terms of susceptibility to COVID. And that is all going into the rate of COVID, but it's not critically the rate by race ethnicity. And so given the population of Detroit, that is Wayne County and its population of Wayne County, which is Detroit and its close-in suburbs, we have a large Black population, a Hispanic Latino population that makes up roughly about 5% of the population. And then we have another 5% that is categorized as other. This would include Asian, Native American. It could possibly include people of Middle Eastern descent, even though according to the census, they're classified as white. And then there's a white population that's a little under 50% of the population according to the 210 decennial census. And of that white population, we're talking Detroit, Michigan, which does have a very, very large Middle Eastern population. The table is giving you the breakdown of what happens when you build these data sets where you have missing race ethnicity in various proportions. And what you see here is we have the proportion of cases where 90% of the cases in the data set do have a known race ethnicity. But because we're differentially dropping out race ethnicity according to race ethnicity, we have different proportions of cases which are observed. And then the true incidence of COVID is going to vary not according to race, but according to the composition of the age-sex composition of that racial category. So on average, the white population is older, therefore they're going to have a higher incidence of COVID. And this plays out in, this is the true incidence, that is, this is what our simulation generated. This is the observed incidence. This is what we saw after we dropped out the racial ethnicity demographic information non-proportionally. So that's the simulated data, and what you're seeing here is that that from the simulated data, it's going to look very differently, different amounts of COVID in the population. And what the simulation study, that's just the setup of creating 200 data sets. So this is really a beautiful, beautiful methodologically sound investigation of why the data, of the behavior of models when the data is not missing at random. So that's the key thing to take away from this paper. They did the work for you. And what they do is they use the complete case model, which is a very common approach to data that has missing observations. Drop out all your observations where you don't have a complete case, and then now you just fit your data using a regular regression model. And because this is disease incidence data, we're going to use a Poisson GLM. And I'll explain Poisson GLM later. If you're not entirely comfortable with this kind of statistical model. So we can look at data which is missing at random, and missing at random would be where the data is really totally missing, not at random, we know that, but we're going to say, oh, we can compute the race, we can impute the race ethnicity using other variables. And the imputation techniques, ad hoc multiple imputation, is just saying, well, we'll roughly, assign things in proportion to their composition in the general population. Gibbs multiple imputation is covered in Andrew Gelman's Bayesian data analysis, and it is a process where you go back and forth between the missing data and then the known data, and you keep bouncing back and forth and refining your estimates of the missing data. And the not missing at random data, which is the model that we care about, is that we build a joint hierarchical model of missingness and disease incidence. And I'm going to cover that, so let's keep going. In the simulation study, this is the results of what happens. So this model bias is just looking at the difference between what the true joint log, the true model's log probability, what the true log probability should be, and what the estimates from the log probability are. So we're using Stan, and we're building these complicated models, but we get one overall number out of the Stan fitted model, which is the joint log density of the posterior distribution, and that's what we're looking at. We're looking at the combination of all of the parameters, all of the estimates made by the model. So we have, to read these 4 different panels, you have to realize that we really have 4 columns, 4 lanes in every panel. And then we have a bunch of colors here where both black and purple are for the multiple imputation models where we say that the data is missing at random. The red is the complete case model where we say throw out any data that throw out any observations that have missing data. And the blue thing that we care about is the model that's presented in this paper. This is the joint hierarchical model, which estimates missingness and disease incidence using all the information that's there all at once. So what you see is that when you only have 20% of the data to work with across all of these 4 populations, the other thing we should remember is that the Black population is about 40% of the general population, and the white population is about 50%, and Hispanico, Latino, and other are both about 5% of the general population. So we have a lot less data for the 2 middle panels. We have a lot more data, a lot more observations from the Black population and a lot more observations from the white population. So the 2 middle panels are showing a lot more variation across all of these models. And the black and white are showing a very similar pattern. And what we want to keep our eye on here is the light blue, which is very hard to see. But basically, what these plots are saying is, gosh, if you build a model that is more or less in line with the reality of the situation, the data is not missing at random, you get a better estimate of what's truly going on. And another way to look at this is if we looked at relative risk. And this is, again, what we really care about in a pandemic situation. How much worse is it for one subset, one subpopulation than it is for another subpopulation? So what you see here is that the estimates of the relative risk for Black versus white for our light blue model, and I know these colors are not easy to distinguish. Trust me, the light blue is the thing on the Black middle line here, and it goes across. And we see that other versus white and Hispanic Latino versus white, the other versus white looks really all over the place. Oh wait, I take that back. The other versus white, the complete case models and the multiple imputation models do not do very well, even when we have most of the data, because for other, we're dropping out the data, the racial ethnicity data, we're dropping it out at a rate that's even greater than the dropout for Black versus white. So for the Hispanic Latino versus white, we just we drop out the data at the same rate for Hispanic as we do for white. So you see that what amount of data you have, if the data is here, the data is really present in the same amount of proportions and the model behaves one way. Here, the data, and you don't have a lot of data for Hispanic population because there aren't a lot of, it's about 5% of the general population versus 50%. Is this entirely clear? So let me go on to the next slide then. To model the disease prevalence, this model is a Bayesian model. It's very, very simple, but it looks kind of mathy. So what we're going to do for a disease process, what you're observing is you're observing the number of cases, and you've got some rate of disease. That's your Poisson parameter lambda. And to get the disease rate, you just take the number of cases in your population and you divide it by the total population. So this is a rate estimate, and the Poisson distribution is the distribution, the probability distribution that matches your data generating model. The Poisson is a little bit problematic because it only has a estimate of the mean, and in the Poisson model it says, well, your mean and your standard deviation are the same, which leads to many problems that people have to work with down the road. But let's just focus on this Poisson distribution. And what we want to do is we want to use the covariates in our data. We want to use all of the features that we have for every observation and build a linear regression model. So what we want to do is we want to build a Poisson linear regression, and the formula for that Poisson linear regression looks like this. Our data is distributed log Poisson according to the sum of the log of the population plus the set of covariates that you have for your data. And to model missingness, what you have is a simple binomial model. This is just the old coin flip model that everybody starts out with, where success, we're going to code success as 1, we're going to code failure as 0, we're going to count the number of trials, number of coin flips, and given the number of coin flips, if you had 5 successes out of 10 trials, then you would be able to estimate that, well, your probability of success is about 0.5. So parameter P, a probability of success, is a probability, therefore it's between 0 and 1. And because we're doing Bayesian modeling here, we need to put priors on our distribution. And for a uniform prior, we would say, you know what? We think the outcome is pretty much 50-50. And that works out from the beta prior because you're going to look at alpha plus 1 trials, and beta is the number of successes. So 1 works out to 1/2, the equivalent of uniform prior. Nothing complicated here, but the notation does look complicated because we've got all of these Greek letters and all of these subscripts because we're looking at stratified data. So continuing on, what we're going to do is we're just going to put this information together. And what we're going to say is that if we have a Poisson regression where we're trying to estimate the disease rate, but we also know that some of our data is missing, we're going to put those two things together so that for every category, every variant, every different stratum and racial category that we're looking at, we're going to weight them by the probability that race ethnicity information will be present or not. That's all that's going on here. If we've seen all the data, we can just weight each cell in our tabulated table of number of COVID cases per number of tests per demographic per population unit. If we haven't seen, if the race ethnicity information is missing, what we want to do is we have a discrete latent variable here. We can't observe what racial category you belong to, but we're going to estimate it. But this is a discrete category. It's just, are you Black? Are you white? Are you Latino? Are you other? And we can't estimate discrete latent variables in STAN. Instead, what we have to do is we have to marginalize over all of the possible outcomes for that particular variable, sum them up, and then we're good to go. We've got an estimate of something that is not discrete, and we can do our Bayesian modeling. And so this is a key point in when you're building a stand model in being able to understand how to handle discrete latent variables by marginalizing over them. And it looks a little complicated just because we got a few indices and a Greek letter sigma. It's really easy. And in the slides, we've linked to the chapter in the Stand Users Guide that gives you a couple of examples of how to do this. And this comes up a lot in your data, so it's good to know. And the simplest possible model is where the missingness at the individual level depends only on race ethnicity, in which case some of our categories can all be sort of glommed together in one, and a lot of these indices drop out. And I'm starting to go a little bit fast because this is in the paper. I'm trying to here give you an overview of where they're going with this paper. Because it's kind of hard to see given the way the paper is written, because they stop after section 2.1, they start making some proofs to show you that this inference is valid. How does this model behave when you have different amounts of data? How does it behave in the limit of no data or lots of data? And this is very, very important in terms of justifying the use of the model. And what they show in the paper is that this model is theoretically sound with certain conditions. The model itself is a very straightforward model. It's what you want to do. It's not what's commonly done. That's really the takeaway of this talk. Rob Trangucci and John Zellner sat down and said, for this COVID data, we're going to build a Bayesian joint hierarchical model. Let's do it, and let's show people that this works. It does. This is the model you should be using the next time around. Now, what you need to do and why this starts to look like a very complicated problem is that you really need to put informative priors on all the variables in your model, and then you're going to need to put priors on those distributions, because this is another distribution here, right? We have a prior on our probability of data being missing from a beta distribution that has its own priors. And then the prior on disease incidence, the rate of disease, is got a gamma. And so now we're going to have to figure out what values we want to plug in here. The values we plug in here are what we're calling hyperpriors or hyperparameters. And the reason that we're calling them hyperpriors, hyperparameters, is that this model is a hierarchy of different variables. We have our likelihood, and then we have priors over all of the quantities in the likelihood. So again, here's our likelihood. Here's the data. The data where we have all of the race information, all of the outcomes for known race and ethnicity, and all of the variables that are conditional. This outcome is conditional on all of these variables. This conditionality is expressed directly in this model, where we now want to build our regression on age-sex strata, because now the rate of missingness is going to vary by age-sex strata, so we need a bunch of predictors to control how much variation we see between the different strata. The rest of this model is the same. The missingness, which is not dependent on age and sex, only by racial category, and then the disease rate here, which again is only dependent on the racial category. So that is the model where you have missingness, which varies by race and age and sex stratum. And if we're if we're going to use this model, we're going to have a bunch of conditions on the data. So this is where things begin to break down if you don't have enough data, which is, we're Bayesian, we're doing this because we don't have a lot of data, but we need a certain amount of data. So the paper is working through all of these conditions very beautifully. And oh yeah, here they are. Okay, so we've got all these conditions, and this looks perhaps mathematically daunting. All we mean is that we're going to have this, our population, the matrix of the population is going to have these are the population by an I by J matrix. Okay, so we have J rows, and in each row, this is the breakdown by racial category. And so what this means is that the proportions of the different strata in each row have to be different from each other so that you don't have a linear combination. So that if, for instance, you had your Hispanic Latino row and you look down to your row of other, and the first row was simply the second row multiplied by 2. If those numbers all were just a linear combination of each other, your matrix would not be full rank and you would be in trouble. So you do have to establish that you have enough information in the breakdown of racial categories across the strata so that the model is going to be identifiable. And likewise for the regression, the predictor. So for your predictor data, you're going to have, and here you've got things tabulated by strata across the, tabulated by strata across the different predictor categories. So every predictor category has to be contributing real information to the model. And given this theorem and the model, we need to set the priors very carefully. And the reason that we need to do this is that if you have a small population compared to another population that's much larger in a minority group, the setting, your estimates, this is the setting the posterior mean for the rate of disease, that is to say what we think the COVID infection rate is, that is very sensitive to the priors. And that's why this model looks complicated. So they take it a full step further and they go for race, age, sex, and geolocation. And the conclusion here is that what we want to do in a situation where it's critical to get accurate estimates is we need to model the true data generating process. And socioeconomic disparities in the system are going to be reflected in the data quality. Data is going to be missing not at random, not missing at random. So we want to build that model. We need to establish that the model is theoretically sound, that if we fit this model, we're going to be able to trust our inferences. And what they do in this paper, and what everybody should be doing always, is look at the data you've collected or the data that you think you're going to collect and build a simulated data set, or build 200 simulated data sets that match the distribution of the data that you think you're going to get for the model, and then see how that model actually fits the simulated data. In the simulated data, you know the real answer. So how well is your model doing? How well does it fit? And the reason you want to use STAN to do this is that the models are complex. STAN is insanely expressive. You can do everything you want to do. they might take time to fit. And therefore, again, STAN is as good as we've got for fitting these kinds of models. And what we really want to do is we want to have better techniques, better models in our pocket, better things to do for the next pandemic when and if it comes along. I'd like to thank Rob Trangucci and John Zellner for sharing their paper with me, and we've had many really great discussions, and I'm going to continue to collaborate with them and try to bring their work to the population of practicing epidemiologists. I want to thank Data Umbrella and R-Ladies for giving me a chance to get this out to you today. I need to thank the Chan Zuckerberg Initiative for giving me support. I'm funded on a grant called EpiStan, where I'm going to be building out more notebooks and more talks around all of the COVID models that we worked on during the pandemic. And I want to thank you for listening. So great. And here are the references and these slides, and it's all linked. And what are your questions? The slides, yes, the slides are linked too. So let me try to find that. Let me see. I think this is what I'm typing in everywhere. Yes, I just put it in the chat.
So Mitzi, while we wait for questions, give people a chance to absorb the talk. I do have some questions about missing data. Do you think, like, how often do you think that missing data is not addressed in a way that it could be compared to what practitioners are using now?
Well, I think that unfortunately, in a lot of situations where you have public health practitioners that are using protocols that have been defined for them ahead of time, that they don't really have a choice. I think that for places like, say, a hedge fund or a sports analytics team where they know what they're doing and they know they don't have a lot of data and that it does matter, that's why they're using STAN and they're building fairly complicated models. So I think that in a lot of situations, the people who have the money, who are building these models and using them to make money, those people know that this is very important and they have it. And they're taking every step they can. Specifically, we talk to a lot of sports analytics teams. So, Tampa Bay is doing really well for a reason. They use STAN. But getting back to places like public health, what we saw during COVID was that epidemiologists are trained on an awful lot of things about the domain. They know way more about diseases and pandemics than we do. But in their training, they don't get a whole heck of a lot of stats. And the statistics they get, the biostatistics, might not be. Bayesian is probably frequentist. And so they're probably working with protocols, methods of analysis that say discard, only do a complete case analysis. So one of the things that we need to do here is we need to go to policymakers and we need to get better Bayesian methods into accepted practice. That's really the goal here.
Sounds like that needs a whole new grant to do that, right?
I think so. Yes. Sampling weights. We've got a sampling weights question. Andrew Gelman on Andrew Gelman's blog just wrote a paper on sampling weights. In this situation, sampling weights, yes, are sampling weights a frequentist concept? I don't know. Sampling weights are the standard way to set up a survey. You're designing your survey. You know that you're not going to have, or you're looking at the data you've collected and you want to generalize your survey to the general population. So you just multiply, or you multiply all of your observed data by some fraction, which could be greater or less than 1. So you upweight or downweight the data that you've collected for the demographics that you care about. This is not a great way to go in some situations. And if you give me a second, I'll try to find Andrew Gelman's blog and send you the link to his latest paper where there's a lot of discussion about this, because basically you really, as Bayesians, and what Andrew's particular domain of expertise is exactly these kinds of political science surveys, where you do want to have to reweight your samples, study designs, and political surveys. You really would prefer to do what's known as post-stratification. So post-stratification is the idea of building the Bayesian model and getting your inferences, getting the full posterior distribution for every cell, every strata, and then just reweighting the posterior inferences by the proportion of the proportionality in the general population. So it's post-stratification because you're reweighting you're reweighting the posterior estimates according to your representation in the general population. This is a very simple thing to do. It really skips all of your survey weights and survey design problems. It can be done automatically, and it's what you need to do when you don't have the time to call in the frequentist statistician who's going to pore over all of your data and do these horrible calculations to get a good set of survey weights, because there aren't.
The next question is from me. Any plans to do a talk on the same topic with a data example?
With a data example, yes, definitely. Yes. I had 45 minutes, okay? This is a very complicated set of concepts to get across to a general audience. If I had a bunch of epidemiologists in the room, I think it still would take 45 minutes. This takes some time to sort of put your head around all of the pieces of the puzzle. So Edwin is asking about the significance of this issue outside the healthcare domain and telecommunications or finance. I think I answered that question, but if you want a follow-up question, please let me know. But yeah, I'd love to do a longer tutorial on this. The reason I'm funded is to put together notebooks and repositories where, given a morning or an afternoon or a full day, I would be able to work with epidemiologists to really get them comfortable doing this kind of analysis for their data.
Well, thank you for presenting here. I know JSM is happening this week, the Joint Statistical the joint statistical meetings in Toronto, Canada. And
Rob is there, yes.
Oh, he is there.
He's presenting this at JSM.
Oh, okay. And so we're like flattered to get it, maybe at the same time or a little bit before. So thank you so much for presenting here. We don't have any other questions because I do think people need some time to absorb what is, all the information. So yeah, thank you so much. And if you have any closing words, Mitzi? No? Okay. All right. With that, we'd like to thank everybody for joining us. So many people stayed till the end. There's certainly a lot of interest here. I see a lot of statisticians in the audience. So it's really nice to see everybody. Thank you for joining us, and we'll have the video posted fairly soon, within a day. Thank you, everybody.